Welcome to the deep dive. Ever feel like you're staring at a huge, complicated map of information?
Yeah, like a blueprint, maybe.
Exactly. And you wish you just had a few keys to unlock the really important parts, get straight to the core.
Uh-huh.
Well, that's our goal today. We're diving into these fundamental algebraic relationships. People call them special products, sometimes identities.
Right. And we're using the source material you shared as our guide, basically finding those keys for you.
Our mission here really is to show you how these core patterns work. They aren't just formulas on a page you have to memorize.
No, definitely not. They're actually super powerful tools. If you learn to recognize them, you can simplify really tricky expressions and speed up calculations, too. The sources really hammer that home.
Okay, so let's unpack the first one. The sources start with multiplying binomials. It looks something like XPM, A, XPM.
Yep.
They show, for instance, 6x plus A, x plus B, expands to 6 by dollars plus A plus BX plus A. Now, that seems, well, logical when you write it out, but what's the big deal? Why is spotting that pattern useful?
Well, the key is consistency. Look at the examples they give, like 6 plus 10 by 7.
Okay.
Instead of multiplying everything out piece by piece, the FOIL method, if you see it fits that 6 plus A, it's supposed to be a structure, or A plus 10 and my dollars is 7 becomes 7.
Oh.
You
Okay.
jump straight to the result. $6 by $80 plus 10, 7x plus 10.
Which is $6 plus 3 by $7, much faster.
Exactly. Or if it was 6 by 10,
Yeah.
it's 7xAA, that's a $10. That's a $10 on Manco 7s. So you get $6 plus like you saying 7x plus saying goes 10 times and then goes 7x plus 7k. It's about seeing how A and B shape the outcome.
I get it. Recognizing the final structure based on those numbers. Okay, that brings us to another pattern the source highlights. Squaring binomials, like A plus B22 or AB22. These feel kind of like a special case of the first one, maybe, but they get their own focus. Why is squaring so important to spot?
Because the result has a very specific, distinct form. When you expand A plus B to 2, that's A plus B times A plus B, right? You get $2 plus AB plus B22, which simplifies to $2 plus 2AB plus B22. The crucial part is that middle term. It's always twice the product of A and B.
Ah, okay, and for AB22.
Same idea, but it's $2 2B plus B22. That middle term is negative. This pattern is super reliable, and like the source shows, it's fantastic for mental math.
Like that 102 and 22 example, instead of grinding out $102 times 102, you spot that 102 is just $100 plus $2.
Exactly. You recognize it fits the O plus B22 pattern.
So $100 plus 22.
Right.
So 100 plus 22 must be 1,100 times 2 plus 22.
Which is a $10,000 plus 400 plus 42. So 104 of 4. Wow. Yeah, no long multiplication needed.
See? And 432 is another great one. You see it as $53.
Fits the AB2 pattern.
Yep. So $502, 2 times 50 times 1 plus 12, 2. That's $2,500 plus 11.
Well, okay, that's genuinely slick. Spotting the setup is everything.
It really is the time saver.
And there's one more major pattern the source covers, which is, well, it's quite elegant. A plus B, AB. The product of a sum and a difference of the same two terms. Oh yeah, this one cleans up nicely. If you multiply it out, and dollar beta plus beta B2
The middle terms, A dollar 2 beta, they just cancel out.
gone, leaving you with just A B2 and 2. The difference of their squares. It's a beautiful simplification.
And again, the source shows this is great for numbers. Like $8.02 from $7.08 looks messy.
But if you notice, $8.22 is $8 plus 0.2 and $7.82.
Ah,
It's $8 of A with $8 and B2.22.
you got it. So the answer has to be $2 B22. That's $82.
$64 is served 2 cents, which is $63 and 2 nil C.
Okay.
That identity makes calculations like that almost trivial.
Pretty much.
And the sources also mention this works backwards too, right? For factoring.
Yeah.
Like seeing 4 by $2, $9Y.
Exactly. You recognize that as 2 by $2, 3y2 do. That's the $2 B2 form.
It must factor back to A plus B, which is $2 plus 3 plus 3.
Precisely. Or you might see something like $2 plus 6 meters plus $9. You check $2 and then D squared, $9 through 3 squared.
And is the middle term $2? So $2 M times 3, 2. Yes, it's $6 millers.
Bingo. So $2 plus 6 meters plus 9dn fits the $2 plus 2ab plus B2 pattern. Which means it simplifies down to just Lurch plus 322. It's not just about expanding, it's seeing the finished shape and knowing its origin.
Yes. Can you spot those squares? Is the middle term twice their product? If yes, you've likely got a perfect square trinomial you can simplify. Seeing the hidden structure.
So wrapping this up, what's the main point from looking at these patterns? The 6PMB types, the squares of Liam B22, and that difference of squares LEP plus BY.
Well, I think the big takeaway is these aren't just abstract rules. They describe how algebra consistently behaves. And the real skill, like the sources show with those number tricks, isn't just memorizing the formula.
It's actually spotting where these patterns apply within maybe a bigger problem or a calculation.
Exactly that, developing that recognition skill.
And for you listening, getting good at recognizing these basic structures can make much more complex algebra feel, well, less intimidating. It's kind of like having X-ray specs for polynomials.
Right, seeing the simple bones inside the complex expression.
Okay, here's a final thought to chew on. How is recognizing these algebraic patterns, like seeing a perfect square trinomial, hiding in an expression similar to spotting patterns elsewhere, like maybe recurring themes in music or shapes in art, or even trends in complex data?
Interesting question.
How else could learning to spot simple, repeatable structures help unlock understanding in other complex areas of life or study? Something to think about.